Good morning, everybody. How are y'all doing?
Good.
Thank you for coming down here. My presentation's on supercomputers. I think it should be interesting. So, a description of a supercomputer is it's capable of doing tens of thousands of times of computing power compared to a desktop, and it costs tens of millions of dollars. They usually take up enormous rooms that are cooled to prevent overheating. They can perform trillions or even thousands of trillions of calculations per second, and they're capable of solving the biggest issues of our society.
Hey, it's Noah from Test.com. So we're here in Austin, Texas. We're South by Southwest. But we heard that on the University of Texas campus, there's one of the most powerful supercomputers in the world. So I'm here with Dan Stanzion, you're the director of the Texas Advanced Computing Center. Is that true? You guys have one of the most advanced supercomputing clusters in the world?
Yeah, we've had several of the fastest machines in the world throughout the years, and our current machine, Stampede, it's been active for about a year and a half now, and is still 7th in the world. It's even 6th about a year ago.
What does that mean when you say you have the 6th most powerful supercomputing cluster?
Yeah, so there's a benchmark we use to rank, not just we, but that we sort of use around the world to rank supercomputers. It's at top500.org. It's an old benchmark where you measure the speed at which a computer can solve a big system of linear equations, how many unknowns, and you scale it up. And so it's really a ranking of how fast you can do math with a decimal point, essentially, on the machine. So we're at about a peak of between 9 and 10 petaflops right now, so 9 or 10 quadrillion operations per second.
Now, compared to a desktop PC, how many times more powerful than consumer computers is that?
So if you buy a high-end Intel server class chip, a single chip is probably 150 or 200 gigaflops, so 150 billion operations per second.
And we're talking sort of petaflops.
Yeah, so at this point, yeah, we're on the order of 1 million times that speed, or maybe 100,000 times that speed. We sort of, in supercomputing, we go a little faster than Moore's Law, the law that says you double every 2 years of performance, because we're also putting together more and more chips to make bigger and bigger machines. So in supercomputing, we tend to go up a factor of 1,000 about every 10 years. So yeah, so the very first petaflop of a machine in the world was just 3 or 4 years ago. And just 10 years before that, we hit the first teraflop machine, 1 trillion operations per second. And in the late 80s was the first gigaflop machine. So we hit 1 billion about 25 years ago. And that's kind of where the desktop scale is now. So you can think of us as building computers that are about 25 years ahead of what everybody ends up with in their desktops and laptops.
That's very cool. A lot of people, when they think about supercomputers, they maybe visualize the Cray computers, this circular system, but that's not how supercomputers are designed these days. They're clusters or network computers. How do you go about designing a supercomputing cluster? What's the hardware they look at?
Yeah, that's very true. Cray is still a player in supercomputing, but even their machines are more like clusters. Those big machines of old, the round ones that you think about in a supercomputer, were when we thought the best way to build supercomputers was to build custom silicon and custom circuits around that and really change the design of the chips. But as you know, there's now a huge commodity market in building server chips where billions and billions of dollars get pulled into the fab. And we've really sort of reached the point where the return on investment in terms of the power that it takes to run a very fast chip doesn't pay off. So what we do instead is build lots and lots of slower chips that we gang together. So increasing the amount of parallelism or the amount of concurrency that happens to the point where now we use hundreds of thousands of processors in a single machine to make them go fast. So the individual processors in a supercomputer aren't really faster, it's just the scale of them. Because we have so many, there's a few factors that go into the design. One is how you connect them all together. You want to have sort of balanced performance between all of those, relatively pedestrian speed processors, but if you're going to spread a big computation across them, you need to essentially make things synchronized. You need a very fast network between them. So that's a big part of the design, is how you connect them together. And then you need to balance the I/O performance. You need to have a file system that keeps up with it. So you're really sort of tweaking those factors, what kind of processors you use, how much you put into a single server, essentially, to balance them with the interconnect and the file system performance.
So Dan, what kind of hardware is in Stampede? What kind of consumer hardware? Is it all CPUs, GPUs, server processors?
So it's actually a mix. We tried to design Stampede to be really a comprehensive system to solve a whole bunch of different scientific needs that fit into it. So the core of the machine, it was integrated by Dell, and the processors are by Intel. So there's 6,400 servers, each of which have 2 Intel Xeon processors in it. And that's sort of the base system that gets us about 2 quadrillion floating point operations of performance, 2 petaflops. The other 7.5 come from the Xeon Phi coprocessors, which are a new technology from Intel. It's in many ways similar to GPU technology, where we have 61 processor cores on a single chip.
Massively
It's on a big
parallel.
PCI card. Yet very parallel, simpler circuits, and therefore more power efficient. Because power is really driving how we move forward. And so we have one of those in every node, and some have 2. We have about 7,000 of those cards to get us the other 7.5 petaflops of performance in the machine. And then we do have some GPUs in the system, which we use for both GPU computing and for data analysis, which we'll talk a little bit more about later, and visualization. Taking all that data and not having to move it somewhere else to visualize it is really important. And then we have another subsystem of very large memory nodes, which use certain kind.
So at first they would just have many CPUs all working together to multiply their speed. Now they're trying to balance between the GPU, the graphics processing unit, and the CPU, since GPUs are capable of doing many equations that are simple equations. The CPU is more capable of doing complex equations. They take the workload off from the CPU, have the GPU do all the simple stuff, and the CPU handles the complex stuff, which divides the workload and enables them to get much faster speeds nowadays. Now there's 3 main methods of using a supercomputer. It's kind of the software you would use within it. The first one is CFD, it's computational fluid dynamics. The second one is Monte Carlo, and the third is discrete ordinates, or also referred to as finite element. The CFD, computational fluid dynamics, is used for calculating how liquids and gases operate with each other. You know, if you wanted to understand a hurricane or understand how the climate changes, you would plug in thousands of factors, atmospheric pressure, temperature, all these different things, and it would calculate a model, a simulation of what could possibly happen. Monte Carlo is a cause and effect system where you're trying to understand how something happened, so you break it down into the smallest increments of change. So you'd start at the very beginning and record every single little minute change. The smaller the variations in between the changes, the more accurate your answer is going to be. So they follow the chain of events until they get their result. Like financial analysis, they would model how money is spent, how people spend money, you know, from the beginning to the end, to understand, you know, stocks and things like that. That's probably the biggest application since most things are driven by money. That's the most incentive thing. They use it for modeling nuclear reactors, how to transport nuclear devices, to understand how those types of materials will interact with other things around them. You know, if a nuclear meltdown happened, how would the radiation spread through the materials of the building? How would it, you know, how fast would it spread through the atmosphere? Things like that. In space, they're using it to understand space radiation. How does space radiation affect people? How does it affect spaceships or space stations, things like that? So it's very important to understand these things. The third one is discrete ordinates or finite element. This uses quantum mechanics, which, if you're familiar with that, it's calculating the probability of things to arrive at an outcome. You take random samples, they need to be random, the more random samples you collect, the better your results are obviously going to be. And basically you add all those, compile all those in the supercomputer, it calculates out how these objects will behave. So I mean, that would also be applied to nuclear radiation, how it spreads, just understanding the interactions between molecules and how they interact with everything else. Some of the applications of these processes, they've recreated the Big Bang to understand how our Earth came to be, our solar system came to be. They use it for understanding earthquakes, folding proteins. If you understand about proteins, the shape of the protein determines its function, and if it's not functioning, it's folded wrong. And so if they can map out how it's folded, how it folded incorrectly, then they can prevent diseases like cystic fibrosis and other diseases. They've used supercomputers to map the bloodstream, which shows you the interactions between what is in your blood, how those things interact with your organs, all that stuff, you know, which is very important. They've modeled things like swine flu, seeing how not only is it created, but how does it spread through, you know, a factory that has pigs, or, you know, in our food industry. Which if they couldn't do that, then our food would die off. They aren't allowed to actually blow up nuclear weapons now. They have to use simulations to test their bombs. So they use supercomputers to test how their bombs are going to do, just to make sure they still will kill lots of people. They use it for forecasting hurricanes, as I said before, and predicting climate change, which probably isn't the most incentivized thing nowadays with issues of things. And I have one more video.
Weather forecasters use them to create the nightly weather report. Airline pilots use them to learn how to fly planes. Experts use them in virtually every industry and discipline. They're computer models. At NASA, scientists use computer models to enhance our understanding of the Earth, the solar system, and the universe. NASA satellites orbiting the Earth relay immense amounts of data back to scientists on the ground, who can then enter that data into computer model simulations.
We have then equations, and then we have computer code, which solves those equations on a day-to-day basis.
NASA is the source for most of the research satellite observations of the atmosphere, land, and ocean.
So the NASA scientists will look at the observational data and make theoretical projections of what a model might look like. And they will build a numerical model based on the data and then run that on our computers and compare that to reality.
With rapid increases in computer technology, models are becoming ever more powerful and sophisticated, allowing us to simulate our complex environment in greater detail. NASA uses a variety of weather models, such as the Goddard Earth Observing System model, or GEOS-5. It creates an extraordinarily high-resolution, realistic-looking view of our atmosphere. These GEOS-5 simulations showcase the model's ability to capture fine-scale cloud features worldwide, like the swirling clouds in the Atlantic Ocean on the coast of North America. The goal of weather models is to give the most accurate prediction of weather over the next week to 10 days. In 2005, when Hurricane Katrina formed over the Atlantic Ocean, scientists wanted to understand the storm. How intense was it? What was its size and structure? And what would be its final path? NASA satellites continuously monitored many aspects of the storm, from wind speed, rainfall, and sea surface temperature, to the storm's three-dimensional structure. get a more complete picture of the storm and predict its evolution, scientists entered the data into a computer model, then high-powered supercomputer capable of trillions of calculations per second crunch the numbers. This process is called data assimilation. Data assimilation is a two-step cycle that repeats itself whenever new data becomes available. In the first step, the model runs forward in time to provide an estimate of the atmosphere. In the second step, this estimate gets corrected using observation. When the cycle begins again, each step building upon the last and accumulating the information from satellite and ground observation. Weather models are updated every 6 hours to include the most current observations for the next forecast. This approach prevents the model from straying too far from reality and acts as a checks and balance system to achieve the most accurate forecast. While weather models predict conditions for up to 10 days, climate models predict trends over much longer periods of time.
The climate models that are run at the NCCS are numerical expressions of the various processes that make up climate. This includes things like land surface, movement of water in the ocean, and movement of air in the atmosphere.
Just as in weather prediction, data assimilation is a way of bringing all the observations of the Earth together to provide an analysis of our climate. One example of this technique is NERA, the modern era retrospective analysis for research and application. NERA incorporates data from the entire satellite record, over 30 years of data. Its results are a data encyclopedia that can be used for research and analysis. NERA can help meteorologists understand the variations associated with specific weather events. While NERA gives a climate picture across decades, the Goddard Institute for Space Studies, or GISS, can extend that view across centuries. GISS models have already unraveled average temperature trends over 200 years. New GISS simulations will cover the last 1,000 years to verify the model's accuracy. They'll also look forward, projecting climate trends to the end of the 21st century. With each satellite launched, we gain millions of measurements that tell us more about our planet. Having so much more data will require increases in computing power to synthesize this information into meaningful representations of the climate system as a whole.
That does take place when we have a tremendous amount of observational data which is captured by our satellites. We have probably the largest collection of Earth science anywhere in the world, and we have this new state-of-the-art computing center. So the combination of the scientists, the data, and the computing puts us in a unique position to enable advances in weather and climate research.
I think that right there is going to be very important in the future. When our entire polar ice caps melt, and we need to understand where the hot water is going to prevent storms, or at least have a heads up on them. That concludes my presentation. Are there any questions?